Hi, I'm Aaron Passy, CTO at Qumulo, and I want to talk a bit about the block subsystem. But before I do that, a lot of the whole purpose of the block subsystem is to actually protect the data. And so to start, we want to talk about the failure rate, the AFR, of the entire storage system. And this is the inverse of the MTTDL, the mean time to data loss. So this is how long a particular storage system will survive, or the chances of it failing in a year. So this is actually, the AFR actually grows with the restriped time. This makes sense. The longer it takes to restripe from a failure, the higher your potential failure rate is. This grows with.
You mean rebuild, really?
Yeah, the rebuild or restripe. Yeah. This grows with the AFR of your components. If your components are less reliable, your whole system will be less reliable. This grows with cluster size. It actually grows with the number of components, really. So the more components you have that can fail, has them, will make the actual AFR of the entire system lower. Or higher, I guess is the case be. And then finally, it shrinks with the protection level. So this is if you have it at +1, or you have a RAID 5 or RAID 6 or +3 or whatever. The more failures you can handle, obviously, the lower your AFR. So the way when people actually build storage today, they actually they start by choosing the cluster size. Which does this, and then we calculate the protection level that you need. That you need to actually support that cluster size. This is what happens today. So, but if we actually make the restripe time much faster, we use good components, we can actually get the same reliability with a lower protection level. And the protection level has several costs. Protection level. If you have a +1 system, it's much cheaper to write to that system. You end up being faster than a +2 or a +3, and it's also lower overhead on disk. So it's a good goal to actually get the most reliability you can at the lowest protection level you want. So I want to talk about how Qumulo does this. I'm going to start by looking at a physical overview of the system and look at how data is laid out on the system and how we do restripes. So we have a shared nothing clustered system. We have a minimum of 4 nodes, so I'll draw that up. Each node owns its own storage. So I'll put a couple disks in each of these. They're hybrid nodes. Each node also has SSDs. I'll put some amorphous amount of SSD over here. They're connected together with a standard networking, 10 or 40 gig networking. So then we need to look at how do we actually lay out data on the system. So what we actually do is we take we put 5 gig chunks. We lay out our data into 5 gig chunks. So we may have one 5 gig chunk on this spinning disk up here. And I'm going to talk about mirroring here in my examples, but the exact same thing works for erasure coding. You would just have a stripe of these 5 gig chunks rather than just a mirror. But in this case, you'll have his mirror will be down here. Then you may have another 5 gig chunk on that disk, but his mirror is on a different drive. So so these are actually contiguous 5 gig chunks on the drive that are linear. So if a drive fails, you read linear data off the drive. You're way up at the high end of that graph, and you're getting very efficient use of the drives.
Assuming there's no actual I/O going on interrupting your sequentially reading and restriping.
Yeah, absolutely. The key is the restripe itself actually uses the drives in the most efficient way. These are the cheapest IOPS that you can use because you're getting the most out of your drives. You're not seeking them around a bunch, and you can interleave the actual user I/O during that time, and get the best use out of the drives. So this
theoretically, I've never seen a storage system actually be that good at it.
You can actually, when you have the really large block size, you actually can have very short command queues. You can have you don't have to actually line a bunch of IOs into the drive.
I'm not arguing that's how people that's not how people should do it. I'm arguing I've worked on way too many storage systems where the rebuild is doing 64K IOs.
Yeah, that's less optimal. So yeah, you have these short command queues, and so you can inject actual higher priority user I/O into that much, and get service much faster.
Yeah, but it's still a many-to-one rebuild.
Yeah.
Or in the mirrored case, a one-to-one rebuild. And what we really want is a many-to-many rebuild.
Right. So that allows us to get the sequential rebuild. Having this layout on the disk where each of these different chunks have mirrors elsewhere in the cluster allows a many-to-many rebuild. So if this particular drive fails, he has mirrors throughout the entire cluster, and you can use every other drive in the system as a source and every other drive in the system as a destination for the data, and get a fully parallelized rebuild.
So you're not rebuilding the failed drive onto a single drive. You're actually striping the rebuild data across the whole cluster as well.
Yeah. Yes, that's true. We actually keep enough spare space in the cluster to be able to restripe the data. So if a drive fails, we guarantee that we have space for it. So in fact, you can fill the cluster to 100% full, pull a drive, and we guarantee that the restripe will succeed. So we get parallel restripe rebuild.
It would seem your mapping table would have to undergo significant transformation during that process as well.
Yeah, so we have a data structure. It's a distributed key value store that keeps this mapping of this particular P store, which I'm going to define what that is in a second. Which chunks of space actually use that P store, and those things that has a different mechanism for update, but that those get updated every time we move one of these things around. But it's a very fast update. So as an example, in our system, we have a 20-node cluster, and we fail an 8 terabyte drive. And it restripes in 20 minutes. This is faster than it takes to read an 8 terabyte drive by a significant margin. So it allows, it gets a very fast restripe time, and you get reasonable, actually that is another benefit I should put. It has a low overhead during restripe.
What's the restripe time when you fail a node in a 4-node cluster? 3 or 4 days?
It's actually about 4 hours. Or, yeah, I mean, it's some number of hours, and it depends just slightly. Because we don't actually restripe data that isn't allocated. So if the cluster's half full, it'll restripe twice as fast. But generally,
And those nodes are the QC24 or QC208?
these are the 208s in this
So
example.
it's a 26 node or 26 drive node system.
Yeah, exactly. And the QC24s are slower because they have fewer drives. But they're a little faster because they're 6 terabyte drives instead of 8 terabyte drives. But so let's compare this to what it looks like in other systems.
So when you calculate something like AFR, what do you consider your cluster size to be? A 4-node cluster, a minimum cluster, or?
We have a Monte Carlo simulation. This is hard. These actually all have sort of nonlinear relationships with AFR. So we have a Monte Carlo simulation that actually ties into our real restripe scheduling code, so that we actually run simulations of failures, doing the actual movement, doing all the data movement, and figure out actual failure rates.
So this is the fixed protection level, or the customer can configure if they want to have a specific data set to have additional protection, like 3-level mirroring of.
Our system has a single protection level for the whole cluster.
Okay.
Having different protections in different parts of the file system never really seemed like a feature that people actually wanted. Because if you ever have the situation where you have some data at +1 and some at +2, and you actually have 2 failures, you end up with a kind of a messed up cluster, even if so you can still access the data that was at +2, but generally the way to fix it is to copy all the data off onto another system, which generally that's not that's not as high availability as people think it is. So it's a lot better to just protect it evenly. So let's look at what else is out there and what it looks like as far as the protection goes. So first, let's look at traditional Scaleout NAS.
Oh, let's not say we did.
So this is the per file protection case. So in this situation, a particular file will have an inode, and then if it's +2 protected, it'll have 3 copies of that inode. And then there's indirect blocks in there, so maybe it'll have a couple indirect blocks, and each of those are actually 3x mirrored. And then finally, at the bottom, you'll have the data, and say it's a +2, so say it's a 3+2 file, and so these guys will have the data here. So the interesting thing here is when it does a restripe, it has to go through every single file and look at the metadata there, look at each piece of metadata and see which blocks live on the drive that's now missing, and then repair it. So to be able to even figure out what's broken, it has to go and do all this small block I/O, looking at the meta blocks, and it's doing seeks of all the drives all over the place to be able to do the restripe.
I mean, I'm not aware of many traditional NAS systems that do data protection on a file-by-file basis.
Well, this is
they
the
write
traditional
the whole
Scaleout NAS, is what I.
Yeah, but I mean, if it's a NetApp or ENX, it's writing the file system on top of RAID, and so there's
Guess it
no
wouldn't be considered
metadata
a
lookups
scale-out,
in
though.
the file system.
Yeah, but those aren't Scaleout.
Oh,
right?
oh, scale out. Sorry.
Yeah. Yes. So I'm going to get to that in a.
Yeah. Okay. I take it back.
So this ends up being very seeky for the drives.
You used traditional with scale out, and those words don't go together.
At this point, it's been a while. It's become traditional. From our point of
Conventional,
view.
I'll give you, but traditional is scale up.
So this thing, small block size. And the other really interesting thing here is the restriped times are proportional to the number of files in the file system, not proportional to the size. So if you have a cluster and you have all 10 gigabyte files on it, it's fast. If you have a cluster that has billions of 4K files, it's incredibly slow. So it's data dependent. So another architecture out there is object.
That would be traditional object, right?
Yeah, it's traditional object. That's newer, so I'm not going to say that.
Thank you, Ray.
All right, just checking. You guys are awake.
My partner's got my butt covered.
So the way object often works is they have something that on each individual node looks like a file system. They maintain their own objects per node, and then to be able to replicate between nodes, to be able to get protection, they do something that looks something like an rsync. It's different than an actual rsync, but it's basically object by object sending files over, eventual consistency and all that. So this actually has the same problem. To be able to do this rsync-like operation, it ends up being small blocks. It's actually doing metadata traversals inside the object store to be able to figure out what data needs to be sent. And it's also data dependent. If you have a ton of small blocks or small objects, you end up having smaller I/O, and you end up having to do a lot more small operations to the system to do a rebuild. So then the final one is us. And to get a picture here, we have a block layer that has the file system built on top of it, and the block layer itself has the protection behind it. And I've described it how we do this. This is, like you said, this is the same thing that NetApp does, the same thing that VNX does. This is the sort of traditional architecture of have a block layer, have a file system on top of it. But what we did is we made that block system scalable, and we made the file system on top of it scalable. And that was that's where our trick comes in. So,
are you doing any sort of data at rest encryption?
We don't do that today.
Okay, is that on the roadmap?
It is. So we don't have a traditional roadmap per se. We have a prioritized backlog of things that need to be done, and it's definitely on that backlog. Because we definitely have talked to customers who need it. And
so you don't have a roadmap; you have a GPS.
Indeed.
So the rebuild time in a conventional NAS or a Qumulo system is a function of block size. Is that how you'd say that?
Well, for us, it's a function of 1 over the cluster size. As if you double the size of the cluster, the restriped time is cut in half. But otherwise is constant. So for any particular cluster, the restriped time is always the same, no matter what the data is on top of it. Because we can do the large block I/O under the covers, no matter what.
I mean, rebuild times for a 6 terabyte disk in a conventional system is days. I mean,
Yeah.
Yeah, sometimes, yeah.
Yeah,
About
if
2 or 2.5
If it's a
days.
1-to-1 or a many-to-1,
yeah.
yeah, that, you know,
Yeah, I mean, the
think
traditional
we've-
systems don't have the parallelism.
yeah, we've reached the point where, you know, we kind of all have to insist on some kind of many-to-many rebuild, whether it's, you know, 3-part chunklet RAID style or something else. But rebuild to one just takes too long.
Yeah. So let's zoom in on one of these chunks and then look at what the data path actually looks like in our system. So we talked about we have a 5 gig chunk of hard drive. And what we actually do is we have a layer of SSD on top of that. So we have a lot less SSD than we have spinning disk in our system, of course. The current hardware we ship actually has either, between 1 and 5% of the storage is SSD today. So what this ends up looking like is we have individual blocks in here. It's a sparse layer. So we can have, in this example, 2 different blocks that are in SSD. All the rest of the data is on the hard drive. And we can control that on a per block basis. We can decide on each 4K block whether or not it's cached or not in that particular example. So we're talking about this example of being mirroring. So let's put a mirror down here. And then from a software construct above this thing is tied together in an object called a p-store. That stands for protected store, which since we have mirroring here, it's now protected. Above that, we have the file system. And above that, the protocol. NFS, SMB, REST, they can all come through this. And so let's look at what happens for a write request. So the data comes in the protocol, it goes down to the file system figures out which blocks to write. It writes those to the p-store, and then it'll actually send a write to both B stores. And when it does that write, it'll put the data in the SSD and then return. And then it'll return the data back. So a durable write in our system coming in over NFS or SMB is considered complete when the data is in SSD. So you get the latency characteristics of SSD for writes. And you can actually write hundreds or you can write gigabytes of data into the SSDs before we ever send anything down to the hard drives. So this can actually, the data can sit in the SSDs for hours, it can sit in there for days. And what this actually does, so this allows fast, so we have fast random writes. This actually reduces fragmentation. We end up doing random writes to the SSDs, but we can coalesce it together and do sequential writes to the spinning disk as the data comes through. So let's look at a read path. So you have a read request that comes in. Actually, we have a read request that comes in, and it gets down, the file system figures out which block to read. It gets down to the p-store. It can actually choose either mirror. In a erasure coded system, it'll choose where the data actually lives in the stripe, or if there's one down, it'll reconstruct. And then it goes down, chooses this layer, and in this particular case, if there's no block in the SSD, then it'll fall through and read from the hard drive and go back. If it finds the data in the SSD, it'll read it from the SSD. So it acts as a cache in this situation.
So I mean, the SSDs aren't specifically mirrored other than for the write data. Is that so? If the read, so when a read comes in, does the data get promoted from HDD to SSD automatically?
It does not. Like right now, the read will just be will be satisfied by the hard drive, send the data back. There's of course a memory cache in front of all these things anyway, and we in fact we have a cache down here close to the disks, and we have another cache close to the protocols, for caching. But right now we don't actually re-promote data back to the SSD. We have we work in an incremental fashion. We ship every 2 weeks, and we constantly tweak our system for performance and for functionality reasons. So this algorithm is evolving in sort of how we cache and how we represent this.
So the SSD is essentially a write buffer.
It's a write buffer that acts as a cache as well.
Right. If the data is in the write buffer, you'll retrieve it from there.
Yeah.
So in this case, the blocks that are sitting in the SSD on one of the P stores, they're effectively going to be replicated in the blocks in the other SSD.
Yeah, they're actually independent. So in our system, you can actually, the process is called eviction, sending data down to the hard drive. But you could actually evict this one and not that one. And they're independent in how it works.
Okay.
Because this unit here is what we refer to as a B store, which is a block store, and it handles the migration itself internally in our code base. So having this cache allows fast random reads for the small stuff. So typically, what would end up staying in the SSDs is your metadata, or at least the hot metadata. If you have virtual machines, it could be the blocks that are hot in that virtual machine. And we can and this again makes it so our hard drives generally see very large IOs, and the SSDs can handle the small IOs.
And data protection is by object replication? Each file stored in multiple places?
The data protection is at this pstore layer. So we have the file system on top of the pstore, and in my example here I have mirroring, but this pstore could also represent an erasure coded stripe in that.
Okay, this pstore could also represent. Does that mean you're shipping?
The erasure coding is not shipping yet, okay. But mirroring is, and it's actually we have a large portion of our team working on erasure coding. It'll be out soon.
Is the P store the 5 gig chunk, or is it a more granular level than that?
The P store is the 5 gig chunk. So what we end up having on a large system is hundreds of thousands of P stores. So if you squint at this and stand way back and look at it, it kind of looks like a SAN with a bunch of LUNs in there, where each of the LUNs is a P store, is what it looks like, logically speaking. But in our system, these things are transactional, and so you can actually write blocks in 5 different P stores and then commit the transaction. We guarantee that they all get written or they all don't.
Okay, can I do 3 copies today?
Not today. No, we currently ship 2x mirroring in our shipping product.
Okay, so if I get a drive failure and then a read error on the remaining drive, it's back to backup. Yes,
for that piece of data, it would be. But again, we're working on erasure coding. Erasure coding will ship at +2 protection and then be configurable going forward.
And then you're also guaranteeing that data within one P store its replicate isn't stored on the same node in the cluster of another P store, correct?
Yeah, absolutely. Like the data is always across node. The protection is always across nodes. Any node can fail, and all your data stays available.
What happens with data larger than 5 gig where it's multiple P stores?
So the file system itself keeps that mapping. So a particular file might be spread across 1,000 P stores in the system. So it's just, the P store is an abstraction in our system to allow us to do this restriping, basically. And so a generalized address, the file system, when it looks at an address, it's got a thing called a P adder, which is a P store address, and that's a P store ID and an offset. Is that it's a tuple of these two, and so that particular address will be able to find anything in our system.
Yeah, P store is logically a RAID stripe.
Yeah.
Yeah, it's or a LUN or something would be how it would look, logically speaking.
So since you have these nicely packaged, evenly sized containers, why aren't you encrypting at that container level?
It's just farther down on our roadmap, or our backlog, as the case may be. It's mostly because our initial customers haven't asked for it. We try to be as responsive as possible to what our customers are asking for, and as that evolves over time, we will continually add those sorts of features. So to recap, this system allows much shorter restripe times. That scales in the good way with size of cluster. It allows high performance access for the small IOs. It reduces fragmentation. It ends up making a much more reliable system that can be built bigger, have the higher performance, and perhaps it's actually cheaper. And that's it for this part unless there's any other questions.
Do you allow any sort of multi-tenancy?
Well, in our system, I mean, we have basically export a single file system, but you can have different mount points that you export, and you can have different permissions like that. But we don't have any specific multi-tenancy features as of now.
Just following on from your question, actually, can you talk a bit about the access control from a management perspective and what levels that you can provide to your administrators and other users?
As far as like permissions on individual files and stuff. So we actually
within the management console itself. So how you actually break down like role-based access control and so forth.
Yeah. So the cluster itself can participate in Active Directory. We have that, or we have local users as far as what you can use to get into the system, and we have an admin account. All of those different users can log into our admin account, but we haven't really got any role-based access controls. We can't really assign particular roles to particular users yet. We haven't implemented that. But a lot of our APIs are related to the analytics, which we'll talk about here. And those things use the permissions on the files themselves to figure out if it can give you the answer that you're asking for. So anything that's file-based actually already, through the API, actually does the proper permission checking on that. The files themselves have ACLs or POSIX permissions.
Do you have quotas on the NFS exports?
We do not have quotas yet.
Since you do a lot from what your material looks like with graphing, and a lot of people want analysts or NOC to have a read-only view, can you email out your graphs on a daily or hourly? Can you do anything like that? So you don't have to give someone admin level just to look at the graphs or basic stuff.
Yeah, we have, so everything's available via REST API, and what a lot of customers have done, and in fact we offer on our community site, is a management console, which basically goes into the REST API and then presents something, and you can put that on a website. And so you actually have this thing, it's a read-only thing that you can have on a website that shows capacity over time, performance over time, and different statistics in this sort of dashboard for the cluster. So through the actual APIs, you can end up doing a console like that, which is what customers have done so far. The actual read-only thing, as far as is probably the first role we will implement when we do role-based access control for our web UI.